Section 3.2, linear functions. A linear function can be described in a few different ways. It has a graph, which is a non-vertical line. It can be written as y equals mx plus b, and it has a constant rate of change. These are three characteristics that kind of actually all say the same thing, just in different interpretations. We can use each of those interpretations to identify whether something is a linear function or not by looking at its graph and be connected to the first one, by looking at its equation, seeing if it can be written as y equals mx plus b, and using a table to determine if it has a constant rate of change. Now, one key thing to remember here is a linear function, we're told, is a non-vertical line. Even though a vertical line is linear, it can't be a linear function because it wouldn't be a function. It would fail the vertical line test. It would have one input with many, many outputs, and that violates our rule of it being a function. So when we say that it has to be a non-vertical line, that's the reason we put that distinction in there. All right, let's take a look at some graphs. Here you see 6 graphs of functions. They are all indeed functions. And we just need to determine which of these are linear and which are nonlinear. So we'll just start at the top left and go through. First we have a horizontal line, and it's a graph of a line and it's non-vertical, so that's going to be linear. First one's good. Top right, we see we have these 3 dots here. And even though they're not connected, they would form a line. So they do have a linear relationship. So even though they're not connected to form a line, the graph is still linear. It's a linear function. Third one, we have a parabola. That's what this is called. You can see pretty clearly this is not straight. This is not a line. Therefore, it can't be a linear function. It's a non-linear function. And that's what we have there. Next example is technically not a line either because it doesn't extend infinitely in either direction. It's a line segment. And yet, because it is a line segment, its graph tells us that this is a linear function. Actually, I put it right up here. Doesn't look good. Our next graph very clearly is a line. It's a diagonal line, the most typical linear function we would expect. So that's going to be a linear function. And then the final one, you see it curves just a little bit. That curvature right there tells me that this is not linear. It's a non-linear function. So that's going to go right here. And that's really the easiest way it can be, is by looking at the graphs. All you have to do is see, is it a line? If the graph is a line, or part of a line, meaning a segment, or maybe if it had one arrow, a ray, or just 3 points that would be all in the same line, then it's a linear relationship. Linear contains the word line. It also contains the word ear, but that has nothing to do with it. Well, so again, just look at the graph, and if it looks like a line, it's linear. And the only time a line would not be a linear function, again, would be a vertical line. All right, let's take a look at some equations. So for equations of linear functions, they can all be written as y equals mx plus b. That means they can be written that way. They might not be written that way originally, but they could be written this way. On the left here, I have a bunch of examples of linear functions. And this first example is the most obvious. It looks very much like y equals mx plus b, which you might remember is slope-intercept form. And y equals 4x minus 2 is a linear function. You see the 4 would be taking place of the m and the negative 2 replacing the b. And the next ones are all still linear functions, even though they don't necessarily look like it. Y equals 9 minus x, you could just move some things around, but you see that there's a y, there's an x, and there's nothing really strange happening. In the third example, even though there are x's twice, you could add 1/3 x to each side, and when you bring that over, you'll be able to combine them and get y equals 4 1/3 x minus 7, and then it's a linear function in the way we like to set it up. Same thing for the fourth example. Add 2/5 x to the 8x, and just move your 3y to the other side, and just try to move some things around, and ultimately you could rewrite it like this. I'm not asking you to rewrite it like that now. It's more just identifying that it is a linear function. And even y equals 14. Y equals 14 is a horizontal line. Therefore, it's a linear function. The only line that's not a linear function would be a vertical line, which we're going to look at in the next set. Not a linear function, right here, this doesn't necessarily mean that these are even all functions. We'd have to look at their graphs to know that for certain, for some of them. The reason that the first one is not a linear function is, we'll learn this later, this is going to require us to multiply x by x. And multiplying x times x gives us x squared. And that's going to be the problem with this one. All right, we can't have an x squared, we can just have an x. In the second example, very similarly, we're going to end up with a y squared. And that's what's problematic there. We can't have a y squared, we're only allowed to have a y. Y equals mx plus b. For the next example, the problem is the square root of x. We can't have a square root of x in our linear function. It just doesn't make any sense. The fourth example, the problem with this is x equals a number. Well, there's no y because this is a vertical line. And we know that a vertical line, although it's linear, is not a function. So it's not a linear function. And then finally, the problem with the last one is that you have x and y next to each other multiplying each other. That doesn't happen with a linear function. If you were to look at the graph of all of these, some would not be functions. All of them except for the vertical line would be nonlinear, and therefore they can't be linear functions. Keep in mind that, well, the vertical line is x equals a number, the horizontal line is y equals a number. That's really written in slope-intercept form, y equals 0x plus 14. So that's why it still follows the same rule as above, but it just looks a little bit different. So pretty much you want to just look for problem areas. Look for such things as exponents, multiplication of variables, square roots or other roots of variables, variables and denominators, or other things that just look different and strange that would prevent it from being a linear function. And if you don't see any of those, then you're probably in good shape and it will be a linear function. Not always, but typically. All right, so let's take a look at some input-output tables to determine if there's a constant rate of change for a function. Pretty much what you do is you just go from each x value to the next and think about what that change has been. For example, from 0 to 2, we increased by 2. From 2 to 4, increased by 2. 4 to 6, increased by 2. That's good. They're all the same so far. What about for the y's? For the y's, 3 to 9 is an increase of 6. From 9 to 27 is an increase of 18. And from 27 to 81 is an increase of 54. I'll put the pluses there. Now, a rate of change, a rate is a comparison of two things. So I'm going to take my change in y over my change in x. I'm going to write as a fraction. I'm going to write 6 over 2. And then I'm going to do the next one, 18 over 2. And the last one, 54 over 2. And I want to know if those are all the same. Pretty clearly, they are not. If I reduce them all the way, this is going to be 3, 9, and 27. And those are not equal, which means that this table, although it's a function, is not linear. All right, so let's take a look at another example. Let's see if maybe the next one will work for us. 14 to 24, we're going to go up 10. 24 to 34, again up 10. 34 to 44, again up 10. Now on the y's, we're going to do 24 to 20 is actually a minus 4. And that's the same thing to get from 20 to 16 and 16 to 12. So now I want to look at the rates. Again, I take the y over the x. So I'm going to do negative 4 over 10, negative 4 over 10, negative 4 over 10. Are those all the same? Yes, they are. And I could reduce them, but I can already see that they are all the same. Therefore, this table represents a linear function because the rate of change is constant. All right, go ahead and do it for the next two and determine if one or both of those, or neither of these, are in fact linear functions. All right, let's see how you did. All right, and so what we can see is that the first table there represents a linear function. The constant rate is going up 2 on y and up 1 on x. Now this would be true even if, for example, I had another column here, which was 5 and 13. Because if that's the case, I'd have an increase of 4 and an increase of 2. And what I'd have to look at there is my rate is still 4 over 2, which would reduce to 2 over 1, and therefore be the same. So in that case, it doesn't have to be exactly the same just when you reduce it. And then finally, my last example is not linear. It's 3 different rates, 3 over 3, or 1, 1 over 3, and 4 over 3, and none of those are the same. And so therefore, that's not going to be a linear function. All right, I hope this makes sense. All right, almost done here. One last thing to talk about. Domain can either be discrete or continuous, and this is something we haven't really discussed yet. If it's discrete, it means that only certain numbers in an interval would be considered, and the graph would be a series of unconnected dots, like my first example here. This is an example of a discrete graph. A continuous domain would mean that we're talking about all the numbers in the interval, and the graph would be connected, like we have here in this second graph. And for word problems, it's often appropriate to determine if a domain is discrete or continuous. In order to do this, one way we could go about it is to ask if decimals make sense based on the problem. We'll see a couple of examples now so that makes a little bit more sense. Let's look at this word problem here. Mr. Calnan drinks from 16.9 ounce water bottles every day. The amount of water in ounces that he drinks, W, is a function of the number of water bottles he buys, B. So first I'd want to be able to write a function for this, and the independent variable is the number of water bottles that I buy, and the amount of water that I drink is the dependent variable. And each water bottle contains 16.9 ounces, so our equation would look like this. W equals 16.9B. By one water bottle, multiply it by 16.9, that's the amount of water that I'm drinking. I'm assuming here that I'm going to finish the entire water bottle and not refill it at all. Now, the question is this going to be continuous or discrete? Well, in the sense of the problem, remember that B is the amount of water bottles that I buy. Does it make sense to buy a decimal number of water bottles? Could I buy 3.7 water bottles? No, that doesn't really make any sense. I could only buy whole number water bottles. I couldn't buy negatives, and I couldn't buy decimals. So this is going to be an example where my domain is discrete. I'm not going to be talking about every point. I'm going to have just a series of dots, and if I fill in a table or use a graphing calculator, I could actually get my graph. And so you can see what I have here. Although they're not connected because it's discrete, they do form a line. And this this point represents if I buy 3 water bottles, I'll be drinking 50.7 ounces of water. And so the domain would be, it appears to be integers greater than or equal to 0. I'm sure there's some upper limit. I'm not going to buy 10 million water bottles in a day, for example, but the graph would continue in this direction, and that's an example of a discrete domain. All right, let's try the next one. All right, let's say Mr. Calnan is now driving to work at 55 miles per hour, the speed limit I'd like to maintain. Now the distance he has driven in miles D is a function of the amount of hours spent in the car T. Using the last example, try to write the function here. and come back and check your work. How'd you do? So there you go. D equals 55t. T is the independent variable. It's our input. And we want to think, is the domain of this discrete, or is it going to be continuous? And so in order to do this, I want to think about whether or not it would make sense to have a decimal number of hours. Well, when I'm traveling, it's not that all of a sudden it's been 1 hour I'm traveling and then another hour that I've traveled. It definitely would be anywhere in between, too. Any minutes and seconds, I'm still traveling continuously throughout there. So this is an example with a continuous domain. I'm going to be looking at every point in an interval, not just certain points. And like before, you can just put find the graph using a graphing calculator or something. And so you can see this line here represents the distance traveled on the y-axis after a certain period of time on the x-axis. And you see 1 hour is just about 55 miles. Somewhere around here, half an hour, you can get the distance there. 3/4 of an hour, you can find all sorts of things. Now, for the domain here, realistically, we probably wouldn't even want to include this going off to the bottom left here, because that would mean a negative distance and a negative time, which doesn't really make any sense. So we can kind of ignore that for now and just say that it would go from 0 to the right and then up. But that's what a continuous domain looks like as opposed to a discrete domain. All right, I hope this is clear.